Intuitively, a higher temperature reduces the probabilities of common tokens, and as a result, increases the probabilities of rarer tokens. This enables models to create more creative responses. Temperature is a constant used to adjust the logits before the softmax transform a Huyen. Logits are divided by temperature. For a given temperature T, the adjusted logit for the ith token is xit. Softmax is then applied on this adjusted logit instead of on xi. Let's walk through a simple example to examine the effect of temperature on probabilities. Imagine that we have a model that has only two possible outputs, A and B. The logits computed from the last layer are 1, 2. The logit for A is 1 and B is 2. Without using temperature, which is equivalent to using the temperature of 1, the softmax probabilities are 0, 27, 0, 73. The model picks B 73% of the time. With temperature equals 0. 5, the probabilities are 0, 12, 0, 88. The model now picks B 88% of the time. The higher the temperature, the less likely it is that the model is going to pick the most obvious value, the value with the highest logit, making the model's outputs more creative but potentially less coherent. The lower the temperature, the more likely it is that the model is going to pick the most obvious value, making the model's output more consistent but potentially more boring. 24 Figure 2.16 shows the softmax probabilities for tokens A and B at different temperatures. As the temperature gets closer to 0, the probability that the model picks token B becomes closer to 1. In our example, for a temperature below 0. 1, the model almost always outputs B. As the temperature increases, the probability that token A is picked increases while the probability that token B is picked decreases. Model providers typically limit the temperature to be between 0 and 2. If you own your model, you can use any non-negative temperature. A temperature of 0. 7 is often recommended for creative use cases, as it balances creativity and predictability, but you should experiment and find the temperature that works best for you. Sampling 91. 25 Performing an argmax function. Figure 2.16. The softmax probabilities for tokens A and B at different temperatures, given their logits being 1, 2. Without setting the temperature value, which is equivalent to using the temperature of 1, the softmax probability of B would be 73%. It's common practice to set the temperature to 0 for the model's outputs to be more consistent. Technically, temperature can never be 0, logits can't be divided by 0. In practice, when we set the temperature to 0, the model just picks the token with the largest logit, 25, without doing logit adjustment and softmax calculation. A common debugging technique when working with an AI model is to look at the probabilities this model computes for given inputs. For example, if the probabilities look random, the model hasn't learned much. 92, Chapter 2, Understanding Foundation Models. 26 The underflow problem occurs when a number is too small to be represented in a given format, leading to it being rounded down to 0. 27 To be more specific, as of this writing, OpenAI API only shows you the log probs of up to the 20 most likely tokens. It used to let you get the log probs of arbitrary user-provided text but discontinued this in September 2023. Anthropic doesn't expose its model's log probs. Many model providers return probabilities generated by their models as log probs. Log probs, short for log probabilities, are probabilities in the log scale. Log scale is preferred when working with a neural network's probabilities because it helps reduce the underflow problem. 26 A language model might be working with a vocabulary size of 100,000, which means the probabilities for many of the tokens can be too small to be represented by a machine. The small numbers might be rounded down to 0. Log scale helps reduce this problem. Figure 2.17 shows the workflow of how logits, probabilities, and log probs are computed. Figure 2.17. How logits, probabilities, and log probs are computed. As you'll see throughout the book, log probs are useful for building applications, especially for classification, evaluating applications, and understanding how models work under the hood. However, as of this writing, many model providers don't expose their models' logprobs, or if they do, the logprobs API is limited. 27 The limited logprobs API is likely due to security reasons, as a model's exposed logprobs make it easier for others to replicate the model. Sampling 93. Top-K is a sampling strategy to reduce the computation workload without sacrificing too much of the model's response diversity. Recall that a softmax layer is used to compute the probability distribution over all possible values. Softmax requires 2 passes over all possible values, one to perform the exponential sum sigma j exj, and one to perform exi sigma j exj for each value. For a language model with a large vocabulary, this process is computationally expensive. To avoid this problem, after the model has computed the logits, we pick the top K logits and perform softmax over these top K logits only. Depending on how diverse you want your application to be, K can be anywhere from 50 to 500, much smaller than a model's vocabulary size. The model then samples from these top values. A smaller K value makes the text more predictable but less interesting, as the model is limited to a smaller set of likely words. Top P in top K sampling, the number of values considered is fixed to K. However, this number BR should change depending on the situation. For example, given the prompt "Do you like music?" Answer with only yes or no, the number of values considered should be 2, yes and no. Given the prompt "What's the meaning of life?" the number of values considered should be much larger. Top P, also known as nucleus sampling, allows for a more dynamic selection of values to be sampled from. In top P sampling, the model sums the probabilities of the most likely next values in descending order and stops when the sum reaches P. Only the values within this cumulative probability are considered. Common values for top P, nucleus, sampling in language models typically range from 0.9 to 0.95, a top P value of 0.9, for example, means that the model will consider the smallest set of values whose cumulative probability exceeds 90%. Let's say the probabilities of all tokens are as shown in Figure 2.18. If top P is 90%, only yes and maybe will be considered, as their cumulative probability is greater than 90%. If top P is 99%, then yes, maybe, and no are considered. 94. Chapter 2, Understanding Foundation Models. 28 Paid model APIs often charge per number of output tokens. Figure 2.18. Example token probabilities. Unlike top K, top P doesn't necessarily reduce the softmax computation load. Its benefit is that because it focuses only on the set of most relevant values for each context, it allows outputs to be more contextually appropriate. In theory, there don't seem to be a lot of benefits to top P sampling. However, in practice, top P sampling has proven to work well, causing its popularity to rise. A related sampling strategy is min-P, where you set the minimum probability that a token must reach to be considered during sampling. Stopping condition. An autoregressive language model generates sequences of tokens by generating one token after another. A long output sequence takes more time, costs more compute, money, 28, and can sometimes annoy users. We might want to set a condition for the model to stop the sequence. One easy method is to ask models to stop generating after a fixed number of tokens. The downside is that the output is likely to be cut off mid-sentence. Another method is to use stop tokens or stop words. For example, you can ask a model to stop generating when it encounters the end of sequence token. Stopping conditions are helpful to keep latency and costs down. The downside of early stopping is that if you want models to generate outputs in a certain format, premature stopping can cause outputs to be malformatted. For example, if you ask the model to generate JSON, early stopping can cause the output JSON to be missing things like closing brackets, making the generated JSON hard to parse. Sampling 95. 29 There are things you can do to reduce the cost of generating multiple outputs for the same input. For example, the input might only be processed once and reused for all outputs. Test time compute. The last section discussed how a model might sample the next token. This section discusses how a model might sample the whole output. One simple way to improve a model's response quality is test time compute. Instead of generating only one response per query, you generate multiple responses to increase the chance of good responses. One way to do test time compute is the best of n technique discussed earlier in this chapter. You randomly generate multiple outputs and pick one that works best. However, you can also be more strategic about how to generate multiple outputs. For example, instead of generating all outputs independently, which might include many less promising candidates, you can use beam search to generate a fixed number of most promising candidates, the beam, at each step of sequence generation. A simple strategy to increase the effectiveness of test time compute is to increase the diversity of the outputs, because a more diverse set of options is more likely to yield better candidates. If you use the same model to generate different options, it's often a good practice to vary the model's sampling variables to diversify its outputs. Although you can usually expect some model performance improvement by sampling multiple outputs, it's expensive. On average, generating 2 outputs costs approximately twice as much as generating 1. 29. I use the term test time compute to be consistent with the existing literature, even though several early reviewers protested that this term is confusing. In AI research, test time is typically used to refer to inference because researchers mostly only do inference to test a model. However, this technique can be applied to models in production in general. It's test time compute because the number of outputs you can sample is determined by how much compute you can allocate to each inference call. To pick the best output, you can either show users multiple outputs and let them choose the one that works best for them, or you can devise a method to select the best one. One selection method is to pick the output with the highest probability. A long-gauge model's output is a sequence of tokens, and each token has a probability compute by the model. The probability of an output is the product of the probabilities of all tokens in the output. 96. Chapter 2, Understanding Foundation Models. 30. As of this writing, in the OpenAI API, you can set the parameter best_of to a specific value, say 10, to ask OpenAI models to return the output with the highest average log prob out of 10 different outputs. Consider the sequence of tokens, I love food. If the probability for I is 0. 2. The probability for love given I is 0. 1. And the probability for food given I and love is 0. 3. The sequence's probability is 0, 2 times 0. 1 times 0. 3 is equal to 0. 006. Mathematically, this can be denoted as follows: P, I love food, equals P, I, times P, I love, times P, food, I, love. Remember that it's easier to work with probabilities on a log scale. The logarithm of a product is equal to a sum of logarithms, so the log prob of a sequence of tokens is the sum of the log prob of all tokens in the sequence. Log prob, I love food, equals log prob, I, plus log prob, I love, plus log prob, food, I, love. With summing, longer sequences are likely to have a lower total log prob. Log prob values are usually negative, because log of values between 0 and 1 is negative. To avoid biasing toward short sequences, you can use the average log prob by dividing the sum of a sequence by its length. After sampling multiple outputs, you pick the one with the highest average log prob. As of this writing, this is what the OpenAI API uses. 30. Another selection method is to use a reward model to score each output, as discussed in the previous section. Recall that both Stitch Fix and Grab pick the outputs given high scores by their reward models or verifiers. Nextdoor found that using a reward model was the key factor in improving their application's performance, 2023. OpenAI also trained verifiers to help their models pick the best solutions to math problems, Kabi et al., 2021. They found that using a verifier significantly boosted the model performance. In fact, the use of verifiers resulted in approximately the same performance boost as a 30 times model size increase. This means that a 100 million parameter model that uses a verifier can perform on par with a 3 billion parameter model that doesn't use a verifier. DeepMind further proves the value of test time compute. arguing that scaling test time compute, e.g., allocating more compute to generate more outputs during inference, can be more efficient than scaling model parameters. Snell et al., 2024. The same paper asks an interesting question: if an LLM is allowed to use a fixed but non-trivial amount of inference time compute, how much can it improve its performance on a challenging prompt? Sampling 97. In OpenAI's experiment, sampling more outputs led to better performance, but only up to a certain point. In this experiment, that point was 400 outputs. Beyond this point, performance decreases, as shown in Figure 2.19. They hypothesized that as the number of sampled outputs increases, the chance of finding adversarial outputs that can fool the verifier also increases. However, a Stanford experiment showed a different conclusion. Monkey Business, Brown et al. 2024, finds that the number of problems solved often increases log linearly as the number of samples increases from 1 to 10,000. While it's interesting to think about whether test time compute can be scaled indefinitely, I don't believe anyone in production samples 400 or 10,000 different outputs for each input. The cost would be astronomical. Figure 2.19. OpenAI, 2021, found that sampling more outputs led to better performance, but only up to 400 outputs. You can also use application-specific heuristics to select the best response. For example, if your application benefits from shorter responses, you can pick the shortest candidate. If your application converts natural language to SQL queries, you can get the model to keep on generating outputs until it generates a valid SQL query. 98 Chapter 2, Understanding Foundation Models. 31 Wang et al. 2023, called this approach self-consistency. 32 The optimal thing to do with a brittle model, however, is to swap it out for another. One particularly interesting application of test time compute is to overcome the latency challenge. For some queries, especially chain-of-thought queries, a model might take a long time to complete the response. Kitapat Kampa, head of AI at Typhon, told me that his team asks their model to generate multiple responses in parallel and show the user the first response that is completed and valid. Picking out the most common output among a set of outputs can be especially useful for tasks that expect exact answers. 31 For example, given a math problem, the model can solve it multiple times and pick the most frequent answer as its final solution. Similarly, for a multiple-choice question, a model can pick the most frequent output option. This is what Google did when evaluating Gemini on the MMLU benchmark. They sampled 32 outputs for each question. This allowed the model to achieve a higher score than what it would have achieved with only one output per question. A model is considered robust if it doesn't dramatically change its outputs with small variations in the input. The less robust a model is, the more you can benefit from sampling multiple outputs. 32 For one project, we used AI to extract certain information from an image of the product. We found that for the same image, our model could read the information only half of the time. For the other half, the model said that the image was too blurry or the text was too small to read. However, by trying 3 times with each image, the model was able to extract the correct information for most images. Structured outputs Often, in production, you need models to generate outputs following certain formats. Structured outputs are crucial for the following 2 scenarios. 1. Tasks requiring structured outputs. The most common category of tasks in this scenario is semantic parsing. Semantic parsing involves converting natural language into a structured, machine-readable format. Text-to-SQL is an example of semantic parsing, where the outputs must be valid SQL queries. Semantic parsing allows users to interact with APIs using a natural language, e.g., English. For example, Text-to-PostgreSQL allows users to query a Postgres database using English queries such as "What's the average monthly revenue over the last 6 months?" instead of writing it in PostgreSQL. Sampling 99. This is an example of a prompt for GPT-4o to do text-to-regex. The outputs are actual outputs generated by GPT-4o. System prompt: given an item, create a regex that represents all the ways the item can be written. Return only the regex. Example, US phone number dash backslash plus 1 backslash S backslash D 3 1 backslash dash S backslash D 3 dash backslash S backslash D 4 user prompt email address dash GPT-40 AZAZ0-9 underscore percent plus dash plus at AZAZ0-9 dash plus backslash AZAZ 2 user prompt dates dash GTP-40 backslash D 1 2 backslash forward slash backslash dash backslash D 1 2 backslash forward slash backslash dash backslash D 2 4 other categories of tasks in this scenario include classification where the outputs have to be valid classes. 2. Tasks whose outputs are used by downstream applications. In this scenario, the task itself doesn't need the outputs to be structured, but because the outputs are used by other applications, they need to be parsable by these applications. For example, if you use an AI model to write an email, the email itself doesn't have to be structured. However, a downstream application using this email might need it to be in a specific format, for example, a JSON document with specific keys, such as title, body, email body. This is especially important for agentic workflows where a model's outputs are often passed as inputs into tools that the model can use, as discussed in Chapter 6. 100 Chapter 2, Understanding Foundation Models. Frameworks that support structured outputs include Guidance, Outlines, Instructor, and Llama. CPP. Each model provider might also use their own techniques to improve their model's ability to generate structured outputs. OpenAI was the first model provider to introduce JSON mode in their text generation API. Note that an API's JSON mode typically guarantees only that the outputs are valid JSON, not the content of the JSON objects. The otherwise valid generated JSONs can also be truncated, and thus not parsable, if the generation stops too soon, such as when it reaches the maximum output token length. However, if the max token length is set too long, the model's responses become both too slow and expensive. Figure 2.20 shows two examples of using guidance to generate outputs constrained to a set of options and a regex. Figure 2.20. Using guidance to generate constrained outputs. You can guide a model to generate structured outputs at different layers of the AI stack: prompting, post-processing, test time compute, constrained sampling, and fine-tuning. The first three are more like bandages. They work best if the model is already pretty good at generating structured outputs and just needs a little nudge. For intensive treatment, you need constrained sampling and fine-tuning. Test time compute has just been discussed in the previous section. Keep on GeneRat-ing outputs until one fits the expected format. This section focuses on the other four approaches. Sampling 101. 33 as of this writing, depending on the application and the model, I've seen the percentage of correctly generated JSON objects anywhere between 0% and up to the high 90%. Prompting is the first line of action for structured outputs. You can instruct a model to generate outputs in any format. However, whether a model can follow this instruction depends on the model's instruction following capability, discussed in Chapter 4, and the clarity of the instruction, discussed in Chapter 5. While models are getting increasingly good at following instructions, there's no guarantee that they'll always follow your instructions. 33 A few percentage points of invalid model outputs can still be unacceptable for many applications. To increase the percentage of valid outputs, some people use AI to validate and/or correct the output of the original prompt. This is an example of the AI as a judge approach discussed in Chapter 3. This means that for each output, there will be at least two model queries, one to generate the output and one to validate it. While the added validation layer can significantly improve the validity of the outputs, the extra cost and latency incurred by the extra validation queries can make this approach too expensive for some. Post-processing is simple and cheap but can work surprisingly well. During my time teaching, I noticed that students tended to make very similar mistakes. When I started working with foundation models, I noticed the same thing. A model tends to repeat similar mistakes across queries. This means if you find the common mistakes a model makes, you can potentially write a script to correct them. For example, if the generated JSON object misses a closing bracket, manually add that bracket. LinkedIn's defensive YAML parser increased the percentage of correct YAML outputs from 90% to 99%. 99%, Bataro and Ramgopal, 2020. JSON and YAML are common text formats. LinkedIn found that their underlying model, GPT-4, worked with both, but they chose YAML as their output format because it is less verbose, and hence requires fewer output tokens than JSON, Bataro and Ramgopal, 2020. Post-processing works only if the mistakes are easy to fix. This usually happens if a model's outputs are already mostly correctly formatted, with occasional small errors. 102, Chapter 2, Understanding Foundation Models. Constraint sampling. Constraint sampling is a technique for guiding the generation of text towards certain constraints. It is typically followed by structured output tools. At a high level, to generate a token, the model samples among values that meet the constraints. Recall that to generate a token, your model first outputs a logit vector, each logit corresponding to one possible token. Constraint sampling filters this logit vector to keep only the tokens that meet the constraints. It then samples from these valid tokens. This process is shown in Figure 2.21. Figure 2.21. Filter out logits that don't meet the constraints in order to sample only among valid outputs. In the example in Figure 2.21, the constraint is straightforward to filter for. However, most cases aren't that straightforward. You need to have a grammar that specifies what is and isn't allowed at each step. For example, JSON grammar dictates that after, you can't have another, unless it's part of a string, as in, key, string. Building out that grammar and incorporating it into the sampling process is non-trivial. Because each output format, JSON, YAML, regex, CSV, and so on, needs its own grammar, constraint sampling is less generalizable. Its use is limited to the formats whose grammars are supported by external tools or by your team. Grammar verification can also increase generation latency. Brandon T. Willard, 2024. Some are against constrained sampling because they believe the resources needed for constrained sampling are better invested in training models to become better at following instructions. Sampling. 103. 34. Training a model from scratch on data following the desirable format works too, but this book isn't about developing models from scratch. 35. Some fine-tuning services do this for you automatically. OpenAI's fine-tuning service is used to let you add a classifier head when training, but as I write, this feature has been disabled. Fine-tuning a model on examples following your desirable format is the most effective and general approach to get models to generate outputs in this format. 34. It can work with any expected format. While simple fine-tuning doesn't guarantee that the model will always output the expected format, it is much more reliable than prompting. For certain tasks, you can guarantee the output format by modifying the model's architecture before fine-tuning. For example, for classification, you can append a classifier head to the foundation model's architecture to make sure that the model outputs only one of the pre-specified classes. The architecture looks like Figure 2.22. 35. This approach is also called feature-based transfer and is discussed more with other transfer learning techniques in Chapter 7. Figure 2.22. Adding a classifier head to your base model to turn it into a classifier. In this example, the classifier works with 3 classes. During fine-tuning, you can retrain the whole model end-to-end or part of the model, such as this classifier head. End-to-end training requires more resources, but promises better performance. We need techniques for structured outputs because of the assumption that the model, by itself, isn't capable of generating structured outputs. However, as models become more powerful, we can expect them to get better at following instructions. I suspect that in the future, it'll be easier to get models to output exactly what we need with minimal prompting, and these techniques will become less important. 104, Chapter 2, Understanding Foundation Models. 36. As the meme says, the chances are low, but never zero. 37. In December 2023, I went over 3 months' worth of customer support requests for an AI company I advised and found that 1/5 of the questions were about handling the inconsistency of AI models. In a panel I participated in with Drew Houston, CEO of Dropbox, and Harrison Chase, CEO of LangChain, in July 2023, we all agreed that hallucination is the biggest blocker for many AI enterprise use cases. The probabilistic nature of AI. The way AI models sample their responses makes them probabilistic. Let's go over an example to see what being probabilistic means. Imagine that you want to know what's the best cuisine in the world. If you ask your friend this question twice, a minute apart, your friend's answers both times should be the same. If you ask an AI model the same question twice, its answer can change. If an AI model thinks that Vietnamese cuisine has a 70% chance of being the best cuisine in the world and Italian cuisine has a 30% chance, it'll answer Vietnamese cuisine 70% of the time and Italian cuisine 30% of the time. The opposite of probabilistic is deterministic, when the outcome can be determined without any random variation. This probabilistic nature can cause inconsistency and hallucinations. Inconsistency is when a model generates very different responses for the same or slightly different prompts. Hallucination is when a model gives a response that isn't grounded in facts. Imagine if someone on the internet wrote an essay about how all US presidents are aliens, and this essay was included in the training data. The model later will probabilistically output that the current US president is an alien. From the perspective of someone who doesn't believe that US presidents are aliens, the model is making this up. Foundation models are usually trained using a large amount of data. They are aggregations of the opinions of the masses, containing within them, literally, a world of possibilities. Anything with a non-zero probability, no matter how far-fetched or wrong, can be generated by AI. 36. This characteristic makes building AI applications both exciting and challenging. Many of the AI engineering efforts, as we'll see in this book, aim to harness and mitigate this probabilistic nature. This probabilistic nature makes AI great for creative tasks. What is creativity but the ability to explore beyond the common paths, to think outside the box? AI is a great sidekick for creative professionals. It can brainstorm limitless ideas and generate never-before-seen designs. However, this same probabilistic nature can be a pain for everything else. 37. Sampling. 105. Inconsistency model. Inconsistency manifests in 2 scenarios. 1. Same input, different outputs. Giving the model the same prompt twice leads to 2 very different responses. 2. Slightly different input, drastically different outputs. Giving the model a slightly different prompt, such as accidentally capitalizing a letter, can lead to a very different output. Figure 2.23 shows an example of me trying to use ChatGPT to score essays. The same prompt gave me 2 different scores when I ran it twice, 3 out of 5 and 5 out of 5. Figure 2.23. The same input can produce different outputs in the same model. Inconsistency can create a jarring user experience. In human-to-human communication, we expect a certain level of consistency. Imagine a person giving you a different name every time you see them. Similarly, users expect a certain level of consistency when communicating with AI. For the same input, different output scenario, there are multiple approaches to mitigate inconsistency. You can cache the answer so that the next time the same question is asked, the same answer is returned. You can fix the model's sampling variables, such as temperature, top P, and top K values, as discussed earlier. You can also fix the seed variable, which you can think of as the starting point for the random number generator used for sampling the next token. Even if you fix all these variables, however, there's no guarantee that your model will be consistent 100% of the time. The hardware the model runs the output generation on can also impact the output, as different machines have different ways of executing the same instruction and can handle different ranges of numbers. If you host your models, you have some control over the hardware you use. However, if you use a 106, Chapter 2, Understanding Foundation Models Model API provider like OpenAI or Google, it's up to these providers to give you any control. Fixing the output generation settings is a good practice, but it doesn't inspire trust in the system. Imagine a teacher who gives you consistent scores only if that teacher sits in one particular room. If that teacher sits in a different room, that teacher's scores for you will be wild. The second scenario, slightly different input, drastically different outputs, is more challenging. Fixing the model's output generation variables is still a good practice, but it won't force the model to generate the same outputs for different inputs. It is, however, possible to get models to generate responses closer to what you want with carefully crafted prompts, discussed in Chapter 5, and a memory system, discussed in Chapter 6. Hallucinations are fatal for tasks that depend on factuality. If you're asking AI to help you explain the pros and cons of a vaccine, you don't want AI to be pseudoscientific. In June 2023, a law firm was fined for submitting fictitious legal research to court. They had used ChatGPT to prepare their case, unaware of ChatGPT's tendency to hallucinate. While hallucination became a prominent issue with the rise of LLMs, hallucination was a common phenomenon for generative models even before the term foundation model and the transformer architecture were introduced. Hallucination in the context of text generation was mentioned as early as 2016, Goyal et al., 2016. Detecting and measuring hallucinations has been a staple in natural language generation, NLG, since then, see Li et al., 2018, Nya et al., 2019, and Zhou et al., 2020. This section focuses on explaining why hallucinations happen. How to detect and measure evaluation is discussed in Chapter 4. If inconsistency arises from randomness in the sampling process, the cause of hallucination is more nuanced. The sampling process alone doesn't sufficiently explain it. A model samples outputs from all probable options. But how does something never seen before become a probable option? A model can output something that is believed to have never been seen before in the training data. We can't say this for sure because it's impossible to comb through the training data to verify whether it contains an idea. Our ability to construct something so complex that we can no longer understand it is both a blessing and a curse. It's hard to devise a way to eliminate hallucinations without understanding why hallucinations occur in the first place. There are currently two hypotheses about why language models hallucinate. Sampling 107. The first hypothesis, originally expressed by Ortega et al. At DeepMind in 2021, is that a language model hallucinates because it can't differentiate between the data it's given and the data it generates. Let's go through an example to illustrate this. Imagine that you give the model the prompt, "Who's Chip Huyen?" and the first sentence the model generates is, "Chip Huyen is an architect." The next token the model generates will be conditioned on the sequence, "Who's Chip Huyen?" Chip Huyen is an architect. The model treats Chip Huyen as an architect, something it produced, the same way it treats a given fact. Starting with a generated sequence slightly out of the ordinary, the model can expand upon it and generate outrageously wrong facts. Ortega and the other authors called hallucinations a form of self-delusion. Figure 2.24 shows an example of self-delusion by the model LLVAV1. 5-7b I asked the model to identify ingredients listed on the product's label in the image, which is a bottle of shampoo. In its response, the model convinces itself that the product in the image is a bottle of milk, then continues to include milk in the list of ingredients extracted from the product's label. Figure 2.24. An example of self-delusion by LLVAV1. 5-7b. Zhang et al. 2023, call this phenomenon snowballing hallucinations. After making an incorrect assumption, a model can continue hallucinating to justify the initial wrong assumption. Interestingly, the authors show that initial wrong assumptions can cause the model to make mistakes on questions it would otherwise be able to answer correctly, as shown in Figure 2.25. 108 Chapter 2, Understanding Foundation Models. Figure 2.25. An initial incorrect assumption can cause the model to claim that 9677 is divisible by 13, even if it knows this isn't true. The DeepMind paper showed that hallucinations can be mitigated by two techniques. The first technique comes from reinforcement learning, in which the model is made to differentiate between user-provided prompts, called observations about the world, and reinforcement learning, and tokens generated by the model, called the model's actions. The second technique leans on supervised learning, in which factual and counterfactual signals are included in the training data. The second hypothesis is that hallucination is caused by the mismatch between the model's internal knowledge and the labeler's internal knowledge. This view was first argued by Leo Gao, an OpenAI researcher. During SFT, models are trained to mimic responses written by labelers. If these responses use the knowledge that the labelers have but the model doesn't have, we're effectively teaching the model to hallucinate. In theory, if labelers can include the knowledge they use with each response they write so that the model knows that the responses aren't made up, we can perhaps teach the model to use only what it knows. However, this is impossible in practice. In April 2023, John Schulman, an OpenAI co-founder, expressed the same view in his UC Berkeley talk. Schulman also believes that LLMs know if they know something, which, in itself, is a big claim. If this belief is true, hallucinations can be fixed by forcing a model to give answers based on only the information it knows. He proposed two solutions. One is verification. For each response, ask the model to retrieve the sources it bases this response on. Another is to use reinforcement learning. Remember that the reward model is trained using only comparisons. Response A is sampling 109. Better than response B, without an explanation of why A is better. Schulman argued that a better reward function that punishes a model more for making things up can help mitigate hallucinations. In that same talk, Schulman mentioned that OpenAI found that RLHF helps with reducing hallucinations. However, the InstructGPT paper shows that RLHF made hallucination worse, as shown in Figure 2.26. Even though RLHF seemed to worsen hallucinations for InstructGPT, it improved other aspects, and overall, human label errors prefer the RLHF model over the SFT alone model. Figure 2.26. Hallucination is worse for the model that uses both RLHF and SFT, InstructGPT, compared to the same model that uses only SFT, Ouyang et al., 2022. Based on the assumption that a foundation model knows what it knows, some people try to reduce hallucination with prompts, such as adding "answer as truthfully as possible," and if you're unsure of the answer, say, "Sorry, I don't know." Asking models for concise responses also seems to help with hallucinations. The fewer tokens a model has to generate, the less chance it has to make things up. Prompting and context construction techniques in chapters 5 and 6 can also help mitigate hallucinations. 110, Chapter 2, Understanding Foundation Models. The two hypotheses discussed complement each other. The self-delusion hypothesis focuses on how self-supervision causes hallucinations, whereas the mismatched inter-NAL knowledge hypothesis focuses on how supervision causes hallucinations. If we can't stop hallucinations altogether, can we at least detect when a model hallucinates so that we won't serve those hallucinated responses to users? Well, detecting hallucinations isn't that straightforward either. Think about how hard it is for us to detect when another human is lying or making things up. But people have tried. We discuss how to detect and measure hallucinations in Chapter 4. Summary: this chapter discussed the core design decisions when building a foundation model. Since most people will be using ready-made foundation models instead of training one from scratch, I skipped the nitty-gritty training details in favor of modeling FAC tours that help you determine what models to use and how to use them. A crucial factor affecting a model's performance is its training data. Large models require a large amount of training data, which can be expensive and time-consuming to acquire. Model providers, therefore, often leverage whatever data is available. This leads to models that can perform well on the many tasks present in the training data, which may not include the specific task you want. This chapter went over why it's often necessary to curate training data to develop models targeting specific languages, especially low-resource languages, and specific domains. After sourcing the data, model development can begin. While model training often dominates the headlines, an important step prior to that is architecting the model. The chapter looked into modeling choices, such as model architecture and model size. The dominating architecture for language-based foundation models is transformer. This chapter explored the problems that the transformer architecture was designed to address, as well as its limitations. The scale of a model can be measured by three key numbers: the number of parameters, the number of training tokens, and the number of flops needed for training. Two aspects that influence the amount of compute needed to train a model are the model size and the data size. The scaling law helps determine the optimal number of parameters and number of tokens given a compute budget. This chapter also looked at scaling bottlenecks. Currently, scaling up a model generally makes it better. But how long will this continue to be true? Due to the low quality of training data and self-supervision during pre-training, the resulting model might produce outputs that don't align with what users want. This is addressed by post-training, which consists of two steps: supervised fine-tuning and preference fine-tuning. Human preference is diverse and impossible to capture in a single mathematical formula, so existing solutions are far from foolproof. Summary 111. This chapter also covered one of my favorite topics, sampling, the process by which a model generates output tokens. Sampling makes AI models probabilistic. This probabilistic nature is what makes models like ChatGPT and Gemini great for creative tasks and fun to talk to. However, this probabilistic nature also causes inconsistency and hallucinations. Working with AI models requires building your workflows around their probabilistic nature. The rest of this book will explore how to make AI engineering, if not deterministic, at least systematic. The first step towards systematic AI engineering is to establish a solid evaluation pipeline to help detect failures and unexpected changes. Evaluation for foundation models is so crucial that I dedicated 2 chapters to it, starting with the next chapter. 112 Chapter 2, Understanding Foundation Models. 1 In December 2023, Greg Brockman, an OpenAI co-founder, tweeted that evals are surprisingly often all you need. Chapter 3 Evaluation Methodology. The more AI is used, the more opportunity there is for catastrophic failure. We've already seen many failures in the short time that foundation models have been around. A man committed suicide after being encouraged by a chatbot. Lawyers submit false evidence hallucinated by AI. Air Canada was ordered to pay damages when its AI chatbot gave a passenger false information. Without a way to quality control AI outputs, the risk of AI might outweigh its benefits for many applications. As teams rush to adopt AI, many quickly realize that the biggest hurdle to bringing AI applications to reality is evaluation. For some applications, figuring out evaluation can take up the majority of the development effort. 1. Due to the importance and complexity of evaluation, this book has 2 chapters on it. This chapter covers different evaluation methods used to evaluate open-ended models, how these methods work, and their limitations. The next chapter focuses on how to use these methods to select models for your application and build an evaluation pipeline to evaluate your application. While I discuss evaluation in its own chapters, evaluation has to be considered in the context of a whole system, not in isolation. Evaluation aims to mitigate risks and uncover opportunities. To mitigate risks, you first need to identify the places where your system is likely to fail and design your evaluation around them. Often, this may require redesigning your system to enhance visibility into its failures. Without a clear understanding of where your system fails, no amount of evaluation metrics or tools can make the system robust. 2. A 2023 study by A16Z showed that 6 out of 70 decision makers evaluated models by word of mouth. 3. Also known as vibe check. For when OpenAI's GPT-01 came out in September 2024, the field's medalist Terence Tao compared the experience of working with this model to working with a mediocre, but not completely incompetent, graduate student. He speculated that it may only take 1 or 2 further iterations until AI reaches the level of a competent graduate student. In response to his assessment, Many people joked that if we're already at the point where we need the brightest human minds to evaluate AI models, we'll have no one qualified to evaluate future models. Before diving into evaluation methods, it's important to acknowledge the challenges of evaluating